Okay, so in the last screencast video on the dot product, we mentioned at the very end that the dot product, it gives us a way of measuring angles between vectors, and in particular, it gives us an easy way of telling whether two vectors meet at right angles, because if two vectors meet at a right angle, then cosine of that angle is equal to 0, and so if the dot product comes out to be 0, well, either one of the two vectors themselves is equal to 0, or the angle between them has to be a right angle, has to be equal to pi by 2, has to be equal to 90 degrees. So we're going to explore some of those geometric implications in this video, and we're going to move on. We've got a couple of videos here to come, and then we'll see kind of how this thing works out. Oops, that arrow is pointing the wrong way. Let's fix that. Okay, so let's say I've got two vectors, v and w. So remember, there's an algebraic definition of the dot product. You just simply multiply the corresponding components, v1 times w1, v2 times w2, all the way down to vn times wn, whatever. You might just have those first two terms if you're in R2. Maybe you've got one more if you're in R3. It's possible you might be in higher dimensions, and then of course, if you want to, you can extend this definition. So we also showed that the dot product could be written in terms of magnitude and direction, right? So somehow these geometric quantities that we associate with vectors, they're encoded within the dot product, because if you kind of view your vectors as arrows, if I have v and I have w, oops, let's put our little hats on those guys, then I can I can determine the plane containing those two vectors, and then within that plane I can measure this angle theta. And so one of the ways I could compute the dot product is, by measuring the lengths of the two vectors and then measuring the angle between them and computing using this formula here. Except, of course, it's usually not actually practical to go out, with a ruler and a protractor or something like this and measure your vectors. What you're usually given is you're given the components, right? You're given the v1, v2, v3, and so on. And so the algebraic definition is generally the more practical definition. It's the one that we're going to work with most of the time. And again, just to remind you, the dot product is always a real number. The dot product is not a vector, it's a number. Make sure that you keep that in mind as we go forward. Okay, so one of the properties that you can show holds for the dot product. While using the dot product, you can show that this result called the triangle inequality holds for magnitudes. Right? So the Cauchy-Schwarz inequality says that for any vectors u and v, the absolute value of the dot product. Remember, the dot product is a number. It might be either positive or negative. We take the absolute value to guarantee that this thing comes out to be positive. It's never larger than the product of the two magnitudes, right? This is what Cauchy-Schwarz says. This is Cauchy-Schwarz right here, right? And this, we can see it from this geometric definition, because remember that cos theta is always between -1 and +1, and so the absolute value of cos theta is always between 0 and +1, and that's essentially the Cauchy-Schwarz inequality. So using the Cauchy-Schwarz inequality, you can prove the triangle inequality, which is really only a relationship among magnitudes. Note in particular the less than or equal to sign. Okay, so be careful. Magnitude is not distributive. The magnitude of a sum is not equal to the sum of the magnitudes. And the way you can see this is, if you think about adding your vectors tip to tail, and in fact this is where the name triangle inequality comes from. Okay, if I draw my vector u, and I draw a vector v, then of course the vector u plus v, their sum, if we add them tip to tail, is sitting there. And so the triangle inequality is simply a manifestation of the fact that the sum of the lengths of any two sides of a triangle always has to be bigger than the length of the remaining side, right? So the length of the side corresponding to u plus the length of the side corresponding to v, that has to be bigger than the length of the remaining side. If it wasn't, then you wouldn't be able to join up your triangle. You wouldn't have a triangle. You'd have 3 line segments that kind of have a hole in them somewhere. So this is not something that we really need in this course, but it's worth mentioning if you are taking calculus courses, if you're going on through calculus, the triangle inequality becomes important there. A lot of results in calculus, if you're trying to actually carefully prove them, a lot of results in calculus rest on this triangle inequality. It's something that comes up all the time. But this is probably the last time we'll have to mention it in this course. Okay. So as we mentioned in the last video, using the dot product you can measure angles, because you can take this equation here and you can simply solve for cos theta, and this gives you a formula for the angle between two vectors. Of course, for this definition to make sense, u and v have to both be non-zero vectors, otherwise the magnitude would be 0 and you would be dividing by 0, and then of course that's always a terrible thing to do. So we don't want to divide by 0. And one of the things to notice here is that for non-zero vectors, and so this is if cos theta equals 0, of course the other way that the dot product could be 0 is if u is 0, or if v is 0. But if we insist that we're dealing with two non-zero vectors, then the only way that the dot product can be equal to 0 is if you have two vectors which meet at a right angle. So the name for vectors that satisfy this property that the dot product vanishes is orthogonal. So this word orthogonal here does kind of include the possibility that one of the two vectors could be equal to 0, but the situation, of course, that we really care about is the case where both of them are non-zero and they happen to meet at right angles. So, for example, let's say u is equal to 2, 3, v is equal to 3 and negative 2. Okay, if I calculate the dot product u dot v, I get 2 times 3 plus 3 times minus 2. Well, that's 6 minus 6. That comes out to be 0. So these are indeed vectors that are orthogonal according to this definition. If we were to plot these guys, u would be here. That's a pretty bad arrow. V would be down here, and the angle between them is indeed a right angle. Okay. So just as one more example, let's say we wanted to compute the angle between these two vectors, just to give us some more practice with computing dot products, computing magnitudes. We calculate the dot product. Let's do the dot product first. U dot v. So we multiply the x components, 2 times minus 1. We multiply the y components, minus 3 times 4. We multiply the z components, 1 times minus 2. So that's minus 2 minus 12 minus 2. We get negative 16 for the dot product. The magnitude of u, we get the square root of 2 squared plus 3 squared plus 1 squared. That's the square root of 14. The magnitude of v, we get the square root of 1 squared plus 4 squared plus 2 squared. Notice I'm not bothering to write down the minus signs because, of course, when we square these numbers, if there was a minus sign in front of them, when you square it, that minus sign goes away. So I'm being a little bit, I don't know, call it lazy, efficient, however you want to put it. I'm skipping the minus signs. Okay. So 1 squared plus 4 squared plus 2 squared, that adds up to give us 21, so we've got the square root of 21. So then, if we wanted to know what is the cosine of the angle between them, we'd say, well, cos theta is equal to minus 16 over root 14 times root 21. And you could leave it like that. If you want to be really keen, you might notice that 14 and 21 are both multiples of 7. So there's a root 7 here, there's a root 7 there. So there's a 7 you could pull out if you really want to, but we can just leave it like that. One thing to notice is that in this case, the cos theta comes out to be less than 0. Anytime the dot product is less than 0, one of the things that tells you is that the angle between the two vectors is an acute angle. So they, if we were drawing them, we would have something that looks like this. Okay, so we'll stop here for this video, and in the next one we're going to start mining this definition of orthogonality, and we're going to see that there are a lot of things you can actually do with orthogonality. So that's where we're going next.